For over 2 decades, astronomers have told us the universe is not just expanding, but the expansion is speeding up. This shocking conclusion was based on one discovery. Distant supernovae appeared dimmer than expected. This single observation led to the idea of dark energy, a mysterious, unseen force that now makes up 70% of the universe, rewriting the laws of physics as we know them. But what if we've missed the real problem? A paper claims that cosmic voids could remove the need for dark energy. The light travelling through these underdense regions might explain the dimming without acceleration. But are we just patching a deeper flaw? Because if voids were causing dimming, we would see it not just in supernovae, but in galaxies too. Yet the Tolman surface brightness test shows no such dimming. How can acceleration be real if its effects only show up in one dataset? Are we solving the wrong problem? If SN1A dimming is an artifact of how we measure them, then dark energy may not exist at all, and that would change everything we think we know about cosmology. In the late 1990s, 2 independent research teams set out to answer a simple but profound question. Is the expansion of the universe slowing down? According to the prevailing model at the time, the universe was expected to be gradually decelerating under the influence of gravity. While it had been expanding since the Big Bang, the assumption was that the combined mass of all galaxies, dark matter, and other forms of energy would be slowing this expansion over time. To test this, astronomers turned to Type 1a supernovae, stellar explosions thought to be perfect standard candles because they always explode with roughly the same intrinsic brightness. The idea was straightforward. Measure how bright these supernovae appear, compare this to their redshift, which is how much their light has been stretched by expansion, and then use this to calculate the distance and how expansion has changed over time. If the universe were slowing down as expected, distant S1A supernovae would appear brighter than expected because they wouldn't be as far away. But in 1998, both the Supernova Cosmology project and the High Z Supernova Search team found something entirely unexpected. Distant S1A weren't brighter, they were dimmer. Not just a little dimmer, but about 25% fainter than predicted under a simple decelerating universe model. This suggested that the supernovae were further away than expected, which in turn implied that the universe's expansion wasn't slowing down, it was speeding up. This was a shocking result. If true, it meant that the universe was not just coasting, it was accelerating. Something unseen had to be driving this process, something that overcame the pull of gravity on a cosmic scale. This unseen force became known as dark energy, and almost overnight it reshaped cosmology. The concept of an accelerating universe driven by an unknown energy making up nearly 70% of the cosmos was born. But was this really the only explanation? While the SN1A results were surprising, they also conveniently solved several long-standing issues in the cold dark matter model, issues that had existed well before supernova dimming was discovered. The age of the universe problem. Before acceleration was introduced, CDM models predicted a universe that was too young compared to the ages of the older stars in globular clusters. Adding acceleration stretched the expansion history, increasing the universe's inferred age to a value consistent with stellar evolution data. The missing matter problem. Observations of large-scale structure growth, LSS, suggested that there wasn't enough total matter, even including dark matter, to explain the observed expansion rate. A universe made purely of matter would decelerate too quickly and fail to match the inferred structure formation timeline. Introducing dark energy allowed for a low total matter density while still matching the LSS constraints. The flatness problem. The cosmic microwave background strongly suggested that the universe was spatially flat. However, matter alone could only account for about 30% of this total density. The addition of dark energy filled in the missing component, ensuring that the universe's flatness matched CMB observations. Because the idea of acceleration conveniently resolved all of these outstanding problems, it was widely accepted with little resistance. Instead of exploring whether SM1A dimming might be caused by alternative effects, cosmologists quickly embraced dark energy as the definitive answer. This is an unusual event in scientific history. Most anomalies are met with skepticism and rigorous testing of alternative explanations before a new fundamental force is added to physics. Yet, with dark energy, the response was immediate acceptance, despite lingering concerns about potential systematic biases in S1A brightness or alternative astrophysical explanations. Even at the time, there were important unanswered questions. Could intrinsic changes in SN1A properties over cosmic time explain dimming? Was SN1A brightness truly independent of redshift? And perhaps the biggest question, if acceleration was real, shouldn't its effects be observed in multiple different cosmic tests, not just in SN1A? At first, these concerns were largely dismissed. The SN1A results matched well with the lambda-cold-arc model, and dark energy resolved multiple pre-existing cosmological tensions. But, as we'll see, not every measurement tells the same story, and the missing piece in this puzzle reveals something far more troubling about the state of modern cosmology. The cosmic distance ladder, the cornerstone of modern cosmology, relies on a multi-step calibration process linking redshift to distance through various astrophysical markers. It begins with parallax measurements for nearby stars, then uses predictable brightness variations of Cepheid variables to reach further galaxies. Techniques like brightness fluctuations and the Tully-Fisher relation refine these measurements, and ultimately Type 1a supernovae extend our scale to the most distant reaches of the universe. Together, these methods construct a redshift-distance relationship, assumed to progress smoothly from our cosmic neighbourhood to the furthest observable objects. Yet, this entire framework hinges on one critical assumption, that redshift and distance follow a well-defined relationship, with standard candles establishing the scale. The problem arises when high redshift S1A supernovae appear unexpectedly dim. Rather than re-evaluating the calibration between redshift and distance, the prevailing response has been to conclude that the universe's expansion is accelerating, effectively altering the distance scale. This leads us to a perplexing oversight. If cosmic acceleration were genuine, then both redshift and luminosity should bear its mark. In reality, while SN1A are dimmer than predicted, their redshifts adhere perfectly to the expected trend for a steadily expanding universe. This discrepancy raises a fundamental question. Why would acceleration impact brightness but leave redshift untouched? If acceleration were real, a progressive deviation would be evident in both measurements. Instead, redshift remains consistent, suggesting that the observed dimming might stem not from acceleration, but from a misinterpretation of SN1A brightness itself. Ultimately, this forces us to reconsider. Are we misinterpreting the intricate relationship between redshift, distance, and brightness? The redshift clustering paradox highlights a significant issue when comparing cosmic acceleration to redshift-distance relationships measured in large-scale structure surveys. If the universe were truly accelerating, earlier epochs should show a compression in redshift space. Galaxies at higher redshifts appear closer together, while more recent epochs should be stretched apart by a higher expansion rate. Yet, in practice, large-scale surveys do not reveal this effect directly. Instead, they impose a curved redshift distance model that assumes the very acceleration it seeks to measure, thereby forcing the expected clustering into the data. This begs the question, if such a model can be tuned to yield the anticipated redshift compression in surveys, why does SN1A data still display a dimming anomaly that is interpreted as evidence of acceleration? The discrepancy can be broken down into several critical issues. First, if the large-scale structure surveys correct for redshift clustering using a predetermined model, one would expect the same correction to apply to SN1A observations. Instead, the anomalies persist, suggesting that the distance scale might be miscalibrated specifically at the epoch where SN1A are measured. Second, while LSS surveys average over statistical clustering of galaxies, smoothing out variations, SN1A rely on precise luminosity measurements that could be more susceptible to systematic errors in redshift distance relation. Finally, there is an inherent inconsistency in methodology. LSS surveys assume a redshift distance curve dictated by acceleration, effectively filtering their observations through this framework, whereas SM1A are used as an independent tool to infer the expansion history. The fact that SM1A reveal a discrepancy not seen in LSS data suggests that the anomaly may not be a true signature of acceleration at all, but rather a reflection of how SN1A brightness and thus distances are interpreted. Ultimately, if the same correction applied in LSS surveys should account for a redshift clustering effect, its failure in the SN1A context indicates that we might be misreading underlying relationships between redshift, distance, and brightness. For over 2 decades, the dimming of Type 1a supernovae has been taken as evidence for cosmic acceleration, an interpretation built on a series of assumptions that rarely receive scrutiny. Yet, a fundamental inconsistency lies hidden in plain sight. If acceleration were a genuine cosmic force, its influence should be universal, affecting not only SN1A, but all brightness measurements across the cosmos. However, when we turn to the Tolman surface brightness test, a completely independent method for gauging how light fades with redshift, we encounter a troubling contradiction. A 2010 study by Alan Sandage and Laurie M. Lubin used the Hubble Space Telescope to apply the Tolman test to 3 distant galaxy clusters at a redshift of about 0.85. Their findings were twofold. On one hand, they observed surface brightness of these galaxies aligned with the expected dimming from a steadily expanding universe. On the other hand, even after accounting for galaxy evolution, the brightness levels remained higher than would be anticipated if the universe were accelerating. In short, there was no additional dimming beyond standard expansion, and no sign of acceleration was detected. This result is especially significant because the redshift range examined by the Tolman test coincides with the range where the SN1A dimming anomaly is most pronounced. If cosmic acceleration were real, it should leave this imprint on every brightness-based measurement within this range, not just SN1A. The absence of extra dimming in the Tolman test suggests that the apparent anomaly in SN1A brightness may stem from how their luminosity is interpreted, rather than from an accelerating universe. This contradiction challenges the very foundations of dark energy. If dark energy drives acceleration, why is its signature detected solely through SN1A? There are several ways to interpret this discrepancy. One possibility is that the universe truly is accelerating, but in a way that somehow only affects SN1A measurements. This scenario would require acceleration to selectively dim supernovae while leaving galaxy brightness untouched, an idea that contradicts the expectation that cosmic expansion should influence all light sources uniformly. Alternatively, the extra dimming might be a measurement artifact rather than a signature of acceleration. For example, SN1A are assumed to be standard candles, but if early supernovae were intrinsically fainter due to factors like lower metallicity, we could mistakenly interpret their dimness as a sign of increased distance and acceleration. Additionally, the complex calibration process encompassing light curve corrections, host galaxy adjustments, and K corrections may introduce subtle biases that mimic an acceleration signal. Another factor to consider is the effect of the intergalactic medium. Interactions between SN1A light and the diffuse gas and plasma that fills the cosmos might cause photons to lose energy as they travel, again making the supernovae appear dimmer. However, this effect should also impact the brightness of galaxies, yet observations show that galaxy luminosities follow the expected trend for a steadily expanding universe. What's even more concerning is that this contradiction has largely been swept aside by cosmologists. The prevailing ΛCDM model assumes dark energy exists, and SN1A results have been neatly integrated into that framework. Instead of re-examining the underlying assumptions, researchers have tended to dismiss any data that conflicts with the model. Science should be driven by following the data, not by bending observations to fit pre-existing theories. Proponents argue that SN1A dimming is evidence of dark energy. They claim that multiple independent methods, such as baryon acoustic oscillations, large-scale structures, and cosmic microwave background analysis, all point to an accelerating universe. However, a closer examination reveals that these methods do not directly measure acceleration. They infer it based on model-dependent assumptions. For example, BAO measurements rely on the ΛCDM framework to interpret galaxy distributions, meaning that if SN1A calibrations were incorrect, the inferred BAO expansion history would also be miscalibrated. The same issue applies to LSS studies, which assume a curved redshift distance relation based on SN1A derived parameters. Another common counterargument is that SN1A dimming has been rigorously corrected for biases including dust extinction, host galaxy effect, and intrinsic variations in supernova brightness. While it is true that many corrections are applied, These adjustments are empirical, not theoretically derived. They are based on matching SM1A to expected behaviour within the expansion model itself. This raises the risk of circular reasoning. Using SM1A to define the redshift distance scale, then assuming that deviations must be due to acceleration rather than questioning the calibration process. Perhaps the most critical rebuttal to SM1A being the sole evidence for acceleration is other brightness-based tests should also reveal this effect. The Tolman surface brightness test conducted with the Hubble Space Telescope does not show unexpected dimming within the same redshift range as SM1A. The standard response is that the Tolman test applies to galaxies, not point sources like SM1A, and that galaxy evolution effects might cancel out acceleration signatures. However, this explanation introduces an ad hoc assumption, that acceleration affects only SM1A but not galaxy surface brightness. If acceleration were truly happening, its effects should be universal across all brightness-based cosmological tests. The fact that only SM1A reveal this effect suggests a problem with how SM1A distances are inferred, rather than definitive proof of acceleration. Ultimately, the counter-arguments defending acceleration rely on a network of mutually reinforcing assumptions, where every dataset is interpreted through the same cosmological model. But if the foundational assumption that SM1A brightness deviations prove acceleration is flawed, then the entire framework built upon it must be re-evaluated. Instead of asking why SM1A appeared dimmer than expected, we should be questioning why no other independent cosmological test confirms this same dimming effect. For over 2 decades, a single observation, the unexpected dimming of Type 1a supernovae, has redefined modern cosmology. The one finding led to the conclusion that the universe's expansion is accelerating, giving rise to the concept of dark energy, now believed to make up nearly 70% of the cosmos. But what if this conclusion is based on a misinterpretation of the data? The original motivation for studying SN1A was to determine whether the universe's expansion was slowing down due to gravity. The idea was that if expansion had decelerated over time, then distant supernovae would appear brighter than expected because they wouldn't be as far away as constant expansion models would predict. But there's a fundamental flaw in this reasoning, one that should have been obvious from the beginning. To test whether expansion was slowing down, astronomers compared the redshift of SN1A to the observed brightness. The expectation was that any deviation from the expected brightness would reveal changes in expansion history. But there's a major problem with this approach. If the universe had been decelerating, or even accelerating, then redshift itself would already reflect this expansion history. By assuming that they could separate redshift from luminosity distance, they ignored the fact that redshift is inherently tied to how expansion changes over time. Any changes in the expansion rate should already be encoded into the redshift distance relationship itself, making the very idea of detecting a separate discrepancy inherently circular. They weren't actually testing for expansion changes, they were testing whether their own distance scales, which assumes a fixed redshift distance relationship, was internally consistent. The most alarming part, the moment they discovered the acceleration instead of deceleration, there was no hesitation in accepting the conclusion. Instead of questioning whether SN1A were truly reliable candles at all redshifts, or whether their distance calibration was circular, or even whether systematic biases could explain the dimming, they locked in acceleration and immediately introduced dark energy as the explanation. This tells us something profound about modern cosmology. Once a model is deeply embedded, observational anomalies are not treated as challenges to the model, they are patches with new theoretical constructs. If the model had been questioned instead of reinforced, the entire narrative of dark energy may have never been adopted. If cosmic acceleration was real, its effect should be universal, appearing across multiple independent measurements. Yet, while SM1A data suggests acceleration, an independent test, the Tolman surface brightness test, confirms expansion without any hint of additional dimming. If acceleration were genuine, why would its signature appear only in SM1A observations? Instead of assuming acceleration and searching for ways to justify it, we should be asking, why does only SM1A exhibit this effect? There are several possibilities. SM1A may not be perfect standard candles, and their intrinsic brightness could evolve over time. Systematic biases in calibration, such as light curve corrections, host galaxy adjustment, and K corrections, may introduce an artificial dimming. intergalactic interactions as SN1A light travels through cosmic structures may cause energy loss in ways not fully accounted for. Each of these explanations could mimic the signature of acceleration. Yet, if any of these factors were at play, why do galaxies observed using the Tolman test remain unaffected? Some have proposed cosmic voids as the solution, suggesting that large, underdense regions might create an inverse lensing effect, making SN1A appear dimmer. But if voids were responsible, then why don't galaxies show the same effect? This leaves us with a stark conclusion. Either acceleration uniquely affects SN1A, which defies our understanding of cosmic forces, or the extra dimming is a measurement artifact. The SN1A discovery didn't just reshape modern cosmology, it revealed a deeper issue. Dark energy was not a prediction, it was a patch. Instead of being derived from first principles, dark energy was adopted to fix the discrepancy in S1A data. Once introduced into the ΛCDM framework, dark energy became an essential component, and subsequent observations were interpreted through that lens, reinforcing the assumption rather than rigorously testing it. This is not an isolated issue. The same pattern has played out multiple times. CMB fluctuations required dark matter to explain galaxy formation. Instead of questioning the assumptions behind structure formation, dark matter was introduced. The Hubble tension suggests a mismatch in expansion rates. Instead of re-examining redshift calibration, cosmologists introduced early dark energy as a fix. SN1A dimming contradicts the Tolman test. Instead of questioning SN1A calibration, dark energy was assumed to be real. Each time an anomaly arises, the response is not to question the foundation, but to add another layer to the model. A model built on interconnected inferences cannot be falsified by a single observation, because every anomaly can be absorbed with a new parameter. If the dimming of SN1A is simply a misinterpretation due to evolutionary differences, calibration issues, or unaccounted intergalactic effects, then the universe might not be accelerating at all. If that's true, then dark energy may not exist, and our entire cosmological model may require fundamental revision. The SN1A distance redshift contradiction isn't just a mistake in measurement, it reveals a flaw in the way cosmology validates itself. The redshift distance scale is assumed to be correct at all scales. This is necessary because the model itself is built upon it. Large-scale structure surveys, BAO measurements, and cosmic expansion history all depend on this calibration. Yet, SN1A studies claim to be testing whether expansion history is correct. If expansion were truly accelerating, it should affect redshift and luminosity together. Instead, they assume redshift remains correct, but luminosity deviates. This means they are comfortable treating redshift distance as both fixed and flexible at the same time. When anomalies arise, like SN1A dimming, they assume distance must be wrong, hence acceleration. But they never allow redshift to be questioned, even though it is fundamentally tied to the same inferred expansion history. This is an internal contradiction that cosmology has never addressed. If redshift distance is fixed, you cannot claim that SN1A luminosity reveals expansion changes. If SN1A luminosity reveals expansion changes, redshift distance cannot be fixed. Yet, cosmologists want to have it both ways. They need a stable redshift distance scale to validate everything else in the ΛCDM, but they also need distance deviations in SN1A to infer acceleration. This selective flexibility is why contradictions like this persist. If one flawed measurement could reshape our entire understanding of the cosmos, then it's time to step back and scrutinize the foundations of our models. If we continue to ignore this contradiction, dismiss alternative explanations, and force data to fit our models, we risk defending dogma instead of pursuing real scientific inquiry. As always, be brave, be curious, the truth is waiting for us. Until next time.